Yeah.
Well done.
It's okay now?
Yeah.
Okay. In this study, we are going to study the turbulent flow around horizontal axis wind turbine rotor blades. The main contributions of this study are in establishing which runs models can produce quantitatively reliable simulations of wind turbine flows and in presenting the flow evaluation over a range of operation conditions. In this presentation, I will go through the following outlines. I will start with the introduction, research motivation, research objectives, model geometry, computational grid, governing equation, then turbulence modeling, result analysis, and finally the conclusions. Okay. A wind turbine, let us first define what is wind turbine. Wind turbine is a device that extracts kinetic energy from the wind and converts it into mechanical energy. Therefore, wind turbine power production depends on the interaction between the rotor and the wind. So, the major aspects of wind turbine performance, like power output and loads, are determined by the aerodynamic forces generated by the wind. Wind blades are usually subjected to two aerodynamic forces as shown in the figure. It is the lift and drag force. The lift usually is normal to the flow direction or the relative velocity. And it is a resultant of different pressure between upper side of the blade and lower side. And the other component, which is the drag force, it is due to the friction force between the circumferential flow around the blade with the blade surface itself. The top of the blade experience faster airflow, and as a result, less pressure experienced. As the pressure on the top of the blade is less than that on the bottom, a resultant force affects towards the lower pressure, leading to produce the lifting force, which I mentioned before. This force is always normal to the relative velocity here, and is tilted by an angle called angle of attack. This is very important, this angle, in order to make a component of the lift force to the direction of rotation, rotating the rotor blade, which lead to generate the moment and then the aerodynamic power. The force which works against the direction of the blade rotation is called the drag force. This one, as I mentioned, it is due to the friction force between the air around the blade and the blade surface. The major goal of mechanical wind turbine is to generate electrical power. The amount of extracted power from the wind never reach 100%. According to Lanchester-Tschikowski limit, the wind turbine rotor cannot extract more than 59% of the power wind. The main aim of this study is assessing runs models available in commercial codes and identifying which ones are suitable for unsteady run simulation of flows past wind turbine and the reason why. And the second aim, using the resulting predictions to advance our understanding of the complex flow physics. In the present work, CFD approach has been employed to provide the detailed information that would help us develop a more complete understanding of the flow process involved, and also more directly in the development of design of more efficient and reliable wind turbine. To achieve this, we need to identify reliable and cost-effective CFD strategies which can produce reliable and cost-effective simulation of three-dimensional unsteady turbulent flows around wind turbine blades. While large simulations can provide reliable flow predictions provided that the mesh is fine enough. If suitable runs models can be identified, then the computational costs and the timescales involved will be substantially reduced. The model geometry which has been used in this study is based on the NREL phase VI horizontal axis rotor blade. NREL, which is National Renewable Energy Laboratory, phase VI wind turbine is the name given to the latest development from the series of combined experiments conducted by NREL since 1987. The phase VI wind turbine rotor is a stall-regulated rotor designed by Giger and Silk, having rated power of 19.8 kilowatt. The phase VI wind turbine rotor has a diameter of 10.058 meter, full span control, and linear tapered and non-linear twist blade. The rotor blade is completely composite of profile section S type S809 from the root to the tip. Starting from here, from the root to the tip of the blade. The computational grid, which has been used in this study, a computational domain of dimensions 24.4 meter height and 36.6 meter width has been generated according to NASA AMIS wind tunnel. As shown here in the figure, we have the computational domain, which is the wind tunnel with the rotating part, which is the cylindrical part here at the middle, in the wind tunnel, with length of 170 meter in the streamwise direction. This length of the wind tunnel is around 170 meter, according to 70 times the rotor diameter. The two-bladed rotor is positioned, this one here, is positioned in the middle of the wind tunnel at a distance of 20 meters from the wind tunnel inlet, according to 2 times rotor diameter. The computational domain for the wind tunnel part and the cylindrical part here, also the blade surface, consist of hexahedral mesh generated by ANSYS ISM CFD software. An all-grid topology is used for the flow field domain and around the two blades and for the blade tips. The governing equations, three-dimensional incompressible Navier-Stokes equation with no heat addition, no mass diffusion, and no body forces can be written in an initial frame of reference using suffix notation as follows. This is the continuity equation, and here the momentum equations. This is the strain rate tensor. And this part, all the parts in the Navier-Stokes equation can be solved easily, except this one, which is the Reynolds stress tensors, which needs modeling, as in the next presentation slides. We will discuss it. In the present study, simulations are basically concerned with rotating. Therefore, it is important to add a term of grid velocity to the continuity equation and the momentum equation in order to account for the rotating in the cylindrical part for the blade. In this study, wide range of turbulence models has been employed in order to model the term which I mentioned, which is the and the Navier-Stokes equation, which is the Reynolds stresses. We have used around 13 turbulence models. Two of these models was high Reynolds number linear eddy viscosity. They are standard K epsilon Reynolds number, and the second one is the realizable K epsilon high Reynolds number model. And then 5 low Reynolds number linear eddy viscosity models. For K epsilon, lean low Reynolds number, shear stress transport, Sst K epsilon fermenter, V2F, K epsilon low Reynolds number, realizable K epsilon 2-layer, and the last one, the Spalart-Almaras, which is one equation model. And also 4 nonlinear eddy viscosity models, which 2 of them is high Reynolds number, and the other 2 is 2 low Reynolds number. So we have here 2 high Reynolds number nonlinear eddy viscosity model and 2 low Reynolds number nonlinear eddy viscosity models. Those are K epsilon lean high Reynolds number nonlinear quadratic model, and K epsilon lean high Reynolds number nonlinear cubic model, and K epsilon lean low Reynolds number nonlinear quadratic model, with the last one here, K epsilon 2-layer lean nonlinear quadratic model. The last 2 models here are 2 Reynolds stress models, Gibson-Launder and Spitzel, Serkar, and Kazusaki RSMSSG models. If you go back to the models, to the 5 low Reynolds number linear eddy viscosity models, these models has similarity to that of Launder and Sherwan, but with additional damping functions. These functions let it be applied in viscous affected regions near the wall. The Sst K epsilon model, the Sst K epsilon model, this one, designed to retain the near wall omega equation with removing its sensitivity to free stream turbulence by using a blending function to switch from K epsilon to near the wall regions to the K omega at the near wall regions to the K epsilon model away from the wall. V2F K epsilon low Reynolds model is this one, solves with K epsilon two more turbulent quantities, the parameters V square, which is used as a damping function for the turbulent viscosity, and the elliptic relaxation function F. The quadratic and cubic nonlinear eddy viscosity models account for anisotropy and sensitize the model to streamline curvature and rotation, which we have in this study due to the curvature of the blade, of course. And also, these models for the Reynolds stress naturally account for anisotropy influence due to rotations and streamlines. The analysis has been done in this study. Here we have two figures which represents the normalized power with inverse tip speed ratio. The inverse tip speed ratio is the dimensionless. Actually, it is dimensionless wind speed. As we can see here, the turbulence of linear eddy viscosity models has been added to the one on the left here, and those of nonlinear and Reynolds stress models, transport models, has been added to those on the right. Both of those figures shows linear relationships or linear increase in the normalized power at lower wind speeds. As you can see here and here, we have linear relationship for the normalized power with the wind speed. And all the models, almost all the models, has a term reliable prediction for the key parameters. But this changed for higher wind speeds, as you can see from here and here, as the models try to deviate from the experimental data. And those two models for Reynolds stress, Gibson-Launder, and also the models for nonlinear high Reynolds number shows quite safe prediction, quite close to the experimental data. This is the three-dimensional animation of vortex structure based on isosurface of Q criteria, Q equal to 5 at different tip speed ratios predicted by Reynolds stress Gibson-Launder model. Here we have three wind speeds: 5 meter, 11 meter per second, 25 meter per second. At low wind speeds, we can clearly see how the flow is stable and no separation from the tip of the blade, except those in the innermost part at the center of the blade. You can see here clearly here, the view is from the section side or from the other side of the blade. We can see no separation at low wind speeds. This wind speed is 5 meters per second, show no separation. This is why most of the turbulent models, which we saw just in the previous slide, most of the, or almost all the turbulent models returned the key parameters, reliable key parameters for the aerodynamic power. But at higher wind speeds, here at 11 meters per second, we can see flow separation starts along the blade. As we can see here, and this is from the section side here, we can see how the flow separation covered till close to the blade surface, which leads to more instability. And this one, the huge separation at higher wind speeds, 25 meters per second along the blade, and also suppress the spiral flow. We can see at low and intermediate wind speed, spiral flow is almost stable, but here has suppressed due to the flow separation, which has extended till to the tip of the blade. As we can see here clearly how the flow separation has covered all the blade surface till the tip of the blade. Exploration of the influence of relevant dimension parameter, the rotational Reynolds number and the tip speed ratio are selected to fully describe each case. Here we can see these two figures comparison, and these figures demonstrate that both these coefficients, which are the rotational Reynolds number, and the tip speed ratio at the same
Sherwan, just warning, it's a 5 minutes because it's the time.
Yeah, I'm going to finish this.
Okay.
Okay. The comparison in these figures demonstrates that both these coefficients at the same tip speed ratios have practically identical value at the two different rotational Reynolds number. As we can see here, each one had different rotational Reynolds number, but had the same on the same line almost. Only the tip speed ratio affected these values. In this study, also we studied the circumferential pressure around the blade using the turbulent model which I mentioned. Here we have CP around the blade at section 30%. From I have separated the pressure, the circumferential pressure, into two groups. The group of turbulent models which doesn't turn any
Can please Dr. Amal or to switch mic off, please. Thank you. Sherwan, we're running out of time, Sherwan.
I think you can come for conclusion.
Okay. Thanks, Sherwan. Have we lost you, Sherwan?
Sherwan, you have to unmute it. Your mic is muted. Please unmute and speak.
Oh, yeah, sorry. At high tip speed ratios, the aerodynamic power increases linearly with wind speed, and all models predict reliable key performance parameters. At lower tip speed ratios, where the relationship between the aerodynamic power and the wind speed becomes nonlinear, the predictions of different turbulence models start to deviate. These deviations are far wider in the case of the simpler linear effective viscosity models. The nonlinear effective viscosity and Reynolds stress transport models show narrower predictive deviations, making them a safer choice. In particular, the Gibson-Launder version of the Reynolds stress model and the two high Reynolds version of the nonlinear effective viscosity models, quadratic and cubic, are the most reliable. Three-dimensional animation of the flow around the rotating blade shows that at low wind speed, the circumferential flow remains attached over both sides of the rotating blade. At higher wind speeds, a flow recirculation bubble is formed over the downward surface of the blade, initially confined to the enormous location and the trailing edge region. As the wind speed increases further, the separation bubble expands in both the radial and circumferential direction to cover the entire downward surface of the blade. Because in absolute terms, the fluid within the separation bubble rotates within the same angular velocity as the blade, the centrifugal force drives the fluid within the separation bubble outwards. When the separation bubble extends over the entire blade surface, this outward motion suppresses the formation of the tip vortex. The flow characteristics and the resulting dimensionless flow parameter are primarily depend on the tip speed ratio. It has thus been demonstrated that, provided that the right advanced turbulence models are used, the cost-effective method of unsteady runs can be used to provide quantitatively reliable prediction of the flow around the wind turbine blades in the downstream wake, and also the dominant frequency of the pressure fluctuation, all of which are critical to the development of more efficient and durable designs. Thank you for your attention. And you're welcome for any question. I'm sorry for the extending the time.
No, you done a great job, Sherwan.